let's talk about the adiabatic process. So, adiabatic process means no heat transfer. Remember, an isothermal process usually has to happen very slowly. The best way for heat to not be transferred is to do stuff really, really fast. So a good example of an adiabatic process is like an explosion, right? There's not time for heat to transfer from one place to another right as the explosion is happening. That is an adiabatic process. So for instance, in your car, you put vapor gasoline into the cylinder, then what do? You ignite it, okay? That is an adiabatic process, all right? The heat doesn't have time to go anywhere because it just explodes and it happens really fast, okay? So things that happen really fast are usually adiabatic. Things that happen really slow are usually isothermal, okay? So if you're reading a problem and it says this thing happens really fast, you can guess it's probably adiabatic, all right? So opening a can, right, a carbonated can, that's an adiabatic process, right? You're changing the volume really quickly, but if there's no time for heat to go in and out of the can because it happens fast.
That is weird. It's weird that it's water coming out of that Pepsi can.
It's probably healthier. Okay, so an adiabatic process looks like this. The curve looks like this. And what does this tell you? It's steeper than an isotherm, and it crosses the isotherms. So that means you have a change in temperature, right? Which means you have a change in thermal energy. But what's zero?
Heat.
Heat transfer, Q,
Oh, yeah.
right? So Q is zero. If you want to go from one point to another, you have to use this. You can't make any of these zero because none of these variables are constant, right? This pressure changes. You can see pressure changes, volume changes, temperature changes too. So we don't get to simplify that too much, okay? But Q is equal to zero, which means if you know the change in thermal energy, that's going to be the negative of the work of the system or equal to the work done by the environment, okay? This is where gamma comes in. It turns out, I won't go through the whole derivation because we're running out of time, but it turns out if you have the pressure here, right, so this is pressure 1, volume 1, pressure times volume to the gamma, remember gamma was either 1.67, 1.4, or 1.3, depending on whether it's a monatomic, diatomic, or polyatomic gas.
Will that be given to us? Or is that
You need to know those three, and it'll tell you if it's a monatomic, diatomic, or polyatomic gas. So, like, for instance, if it says that it's helium, what kind of gas is that? Monatomic. Okay, if it says that it's nitrogen, what kind of gas is that? Diatomic. And I think if it's polyatomic, I'll just say it's polyatomic. Yeah. If you haven't taken chemistry and you're stuck on which one it is, just ask me. But if it's anything on this will be showing. If it's anything on that far right column, that's going to be monatomic. If it's anything this way, that'll either be diatomic or polyatomic. Okay. All right. So this is all you need to write down on your card for an adiabatic process, aside from what it is. Okay, these are all the formulas you would use to calculate a diatomic process. Now, calculating the work, that's a little bit trickier because you have to actually go back to P dV, then you solve this for V, there's a gamma, and the integral gets ugly. Okay, so it's usually easiest when you're doing these problems, in this class at least, to calculate the thermal energy and just know that it's equal to the work. Okay, all right. There's our adiabatic process. Shall we do a problem?
What does T1 V1 gamma minus 1 give us then?
T1 V1 gamma minus 1? That's how you go back and forth between, like if you know the pressure and volume at the beginning, and you, like let's say you knew pressure and volume here, and they gave you the pressure here and they wanted you to calculate the volume, you'd use this.
Okay.
And so this would be like, let's say this is a monatomic gas. This would be pressure. So let's say it's atmospheric pressure. So 101 kilopascals times volume. Let's say it was 0.0224, but it would be 0.0224 to the 1.67.
Oh, okay.
So you'd have to say 0.224 to the, and so people screw this up a lot because a lot of you guys don't remember how to do exponents that aren't like a 2 or a 1/2. So remember how to add and divide things with exponents, right? If you don't remember, please review that. I'm sure Khan Academy has a nice video on it or something, okay? But you're going to want to be able to go back and forth using these gammas. And gamma, remember, has 3 possible values. If it's monatomic, it's 1.67. If it's diatomic, it's 1.4. And if it's polyatomic, it's about 1.3. Okay? All right. Oh, we have an extra 15 minutes. It's Monday. Cool. All right, let's do a problem.
So here we're going to really work on the adiabatic process. We have air that contains gasoline. Sorry. Air that contains gasoline, which is a diatomic gas. That's already giving us a hint about something we're going to need later. So diatomic gas, remember, if we have a diatomic gas, that means our gamma value is going to be 1.4 for diatomic. And you have a cylinder. This is in an engine. We have standard atmospheric pressure. Oops. Which means 101 times 10 to the third. And we also have a temperature of 30 degrees Celsius. We want the piston to rapidly compress the gas, and rapidly is the key word here because that tells us this is an adiabatic, and it even specifically says no heat is transferred. So both of these things should tell you rapid, oops, not rapid, rapid and no heat means adiabatic. We have our volumes. So here's our volumes. We go from 500 centimeters cubed to 50 centimeters cubed, which is a ratio of 10, so you don't necessarily have to divide that yourself. And we want to figure out the final temperature and pressure of the gas in part A. So in part A, we'll write down the stuff we know. So we have an initial value for pressure of 101 times 10 to the third pascals. We have an initial volume because it's a compression, so that's 500 centimeters cubed. We have an initial temperature that is written of 30 degrees C. And we also know that gamma is 1.4 because this is a diatomic gas. So looking at our equations for an adiabatic process, we have this ratio, so pressure final, which in this case would be pressure 2 because we're going from 1 to 2, times volume 2 gamma is equal to pressure 1 volume 1 gamma. We also we know for all PV equals nRT, if we have a constant n, so this is a closed system, so moles aren't getting in and out, molecules aren't getting in and out, we can always use P1 V1 over T1 is equal to P2 V2 over T2. This one is true just in general. Oops. For every state, sometimes we just cancel some of these, like if we have constant pressure, we can get rid of the P. And this one is true for adiabatic processes, and this one's a little bit trickier. So we can rewrite this one to solve for P2, and that's going to be P1 V1 over V2 to the gamma. Okay, so we can plug in our numbers, but that gives us 101 times 10 to the third pascals. And remember, our ratio, our compression ratio, is going to be 10 because we have 500 over 50, so we don't need to convert, it's a ratio. And then this is to the 1.4. So this is going to give us a value of 2.4 times 10 to the 6th pascals. Okay, so that's P2. That's our first thing we're asking for. And then if we want temperature, we just use this equation. So we say, okay, T2, we can solve, and that's going to be T1 P2 V2 over P1 V1, and we know all of those values now because we have our pressure too. So this is going to give us, remember 30 is the same as 303 Kelvin, so 303 Kelvin, and then this is 2.54 times 10 to the 6th over 101 times 10 to the 3rd, both pascals, but remember this is a ratio, and the ratio of volume 2 to volume 1 is going to be 1 over 10. So remember the units of these will cancel, even if you use pascals and centimeters cubed, and this should give us 761 Kelvin, which is a much higher temperature. So for part A, we have our values. So let's say part A looks like this. For part A, we have pressure 2 and temperature 2. Okay. For part B, we want to draw the PV diagram. So let's say and then so here's our pressure, here's our volume. We have our two adiabatic things, but let's start, okay, so we have 50, let's do this in centimeters, 50 and 500. Volume is in centimeters cubed. And then we go from 1 atmosphere or 101, let's call this kilopascals. So 101 kilopascals to something like 2400 kilopascals. Okay, so we want to draw our isotherms. So we'll have one sort of here and one sort of here. Right, here's our two isothermal curves. We start with our initial, oops, I think I did that wrong. Hang on. I want to draw these better. So our initial value should be here. So that means the isotherm has to go through it. So that's why I messed that up. Okay, so isotherm, we'll make that this. So that means this looks like something like this. Oh, it's terrible. Okay, and then at some later time, something more like this. These are very badly drawn. Here, let me try this one more time. So here we have a curve that looks like this, and then some other curve that looks like this. There we go. Those are our two isotherms. This one is going to represent your initial temperature, which is 303 Kelvin. And this is your final temperature, which is 761 Kelvin. And then in between those two things is where we get our actual process. So this connects to this, and it's going in this direction. So here's point 1, so point 1, point 2. This is our adiabatic curve. It's not drawn very well. Sorry about that. But this is what our graph looks like. And that's part B. So here's the PV diagram. These curves should be smoother, but I'm not great at drawing, so you'll have to just bear with me on this one. All right. Part C asks the work done to compress the gas. So let me just move this up a little so we have some space. And we're going to figure out part C. So in order to get the work, remember Q is 0 for all adiabatic processes. So the first law says, the first law of thermodynamics says change in thermal energy is equal to work plus Q, where now we know that Q is 0. We also know that the change in thermal energy is always NCV delta T. So that means that change in thermal energy equals work, which means that work also equals this. So that we can write this as work is equal to NCV delta T. And we have delta T, but the bigger problem is we don't have N. But we can still easily get N from our good old PV equals nRT. So we solve that for N, and that's PV over RT, and we could do that for any point, so either point 1 or point 2. In this case, we're going to use point 1, so P1, V1, T1, because we know all of those. We could also plug in P2, V2, T2. You just can't mix 1 and 2. So that's going to look like 101 times 10 to the third pascals times our volume 1, which is 500 centimeters, so 500 times 10 to the negative 6 meters cubed. Remember, that's the conversion from centimeters to meters because you have to cube it. 8.31 joules per mole Kelvin. For R, that's our constant, and then 303 Kelvin. All of this together gives you 0.0201 moles, which means we can plug into this, so we get 0.0201 moles. Our constant volume is 20.8, which is given to us, which joule per mole Kelvin. And then that also needs to be multiplied by 303. Sorry, we're running out of space. Let me move this. T, that's going to be 761 minus 303 Kelvin. And so when you actually plug that in, that gives you 192 joules, which is the amount of work done to compress the gas. And since it's work done by the environment, if you're looking at this as the environment, you can call it positive. If you're asking for work done by the system, it would be negative. All right, so just to review, we were able to use our equation for adiabats. Remember, an adiabatic curve is always steeper than an isothermal curve, so when you're looking at your graph, if it's compression, you want the volume to be getting smaller, and also work in this case is equal to the change in thermal energy because Q is 0.
Okay, so just to think about this in terms of the first law of thermodynamics, we're going to go through some special cases. So remember, the first law of thermodynamics is just the change in thermal energy is equal to heat plus the work done by the environment. Okay, so here we have this setup thing. So for an isochoric process, we lock the volume. Okay, so we put a little pin in so the piston can't move up and down. That means our change in volume is 0, which means our work is inherently 0. So if we change the temperature, right, like by, in this case, putting ice here, so that means heat is going to leave the system and we're going to go from a higher temperature to a lower temperature. And if you want to draw that on the bar chart, that means we are going to have a negative heat because heat is leaving the system. That takes us from a higher thermal energy to a lower thermal energy, a higher temperature to a lower temperature, okay? For an isothermal process, we could put the gas over the fire and slowly remove the masses, okay? An isothermal process means our change in thermal energy is 0, so our starting and ending thermal energy should be the same. So as we slowly remove the masses, we're adding heat, so, and then we're making sure that the masses get removed so that the temperature stays the same. So, we know the temperature stays the same, which means the work done by the environment is negative because the gas is expanding, so it's pushing against the environment. And then we know because the temperature is kept the same, the thermal energy doesn't change. So your yellow bars are the same size at the beginning, at the end. Okay. Last but not least, we have an adiabatic process. So we insulate the gas completely and allow the process to happen quickly. That means the change in heat has to be 0 by definition. Okay, so let's say we add a mass here, so that changes our work, right? The work is done by the environment. There's forces coming from outside pushing down on the gas and compressing it. So since we start with a particular temperature, that means we should end up with a larger temperature. So as the work done by the environment is negative and the heat is 0, we're going to end up with a larger ending temperature. So the change in thermal energy has to be equal to the work done by the environment. Okay, so here's a question. Which of the following describes what's shown in the PV diagram? Remember, so this is take a minute and look at it. Okay, so the answer is going to be C. So we start with a particular temperature. You can see that there's going to be work, right? So this is going to be work. The work here, because this is an expansion, is done by the gas. Therefore, it is a negative environmental work. So you have negative work. Your change in heat, because this is a constant pressure process, will be NCP delta T. So that's going to be positive heat. So negative work, positive heat, and that means we're going to have a change in thermal energy at the end.